This conference will now be recorded.
Hello everyone. The topics we are going to discuss today: aluminium chloride and alum. So these two are the only compounds that are left. So we are basically discussing different compounds of boron and aluminium under group 13. And under boron we have seen B2H6, borax, and H3BO3, that is boric acid. And for aluminium we have seen AlCl3, that is aluminium chloride. The preparation part we have finished in the last class. Today we will start with its structure and after that properties and uses. Once it is finished, then there will be the next compound, which is alum. So aluminium chloride, what is its structure? Now as you can see in this picture, we have different structure depending on what is its physical state. So when it is solid state, we have this type of crystal structure, where if we enlarge this part, you will be able to understand that the gray color part, that part is basically aluminium, and surrounding it there is total 6 coordination. So here octahedral arrangement is present in the crystal structure, and this structure of aluminium chloride we get, that is cubic close packed layer structure with octahedral coordination, where surrounding a single aluminium there will be total 6 chlorine atoms. So this is the coordination found in when it is in solid state. But when it is in liquid state or molten state, now the dimer form is important. Fine. So it exists as a dimer with tetrahedral coordination geometry. So sometimes it is also in gas phase, because when we say gas phase, it is not that particular temperature. There may be low temperature gas phase or high temperature gas phase. So for low temperature gas phase, liquid state and molten state, we get this type of dimeric structure. And this type of dimeric structure, as you can see here, this part is aluminium, just compared with this structure, that is the picture which is above it. Here 2AlCl3 together is forming this dimer. So if this is aluminium and this part, if it is in one plane, then this plane, it is perpendicular to this. So tetrahedral arrangement surrounding aluminium you can see here. So that is what is written here, tetrahedral coordination geometry. And when it is high temperature gas phase, now this dimeric structure is also not there. Now it is broken and we have this type of monomeric structure of AlCl3. Fine. So these dimers now will dissociate into trigonal planar geometry. So this is trigonal planar. In the same plane, all these 4 atoms are present. Now for the dimeric structure, we'll try to see how the electron deficiency of monomer unit is removed. So the purpose why they form dimers is to remove electron deficiency. As you can see here, when it is monomer AlCl3, the electrons that are coming from chlorine, that is in violet dots, and the electrons, that is the valence electrons, that is for aluminium, it is in cross sign. So there are total 3 bonds present, that is 3 aluminium chlorine bonds, and these 3 aluminium chlorine bonds, here 1 electron is coming from chlorine, another electron is coming from aluminium. So it is normal 2 center 2 electron bond. But if you look carefully, surrounding aluminium, there is total 6 electrons present, 2, 2, 2. These are the lone pairs of chlorine that are not used for bond formation, but surrounding aluminium, total number of electrons only 6. It means that octet is not complete, and if octet is not complete, then to remove this electron deficiency, now it forms dimer. Now if you look at this dimeric structure, just compare this with this, because in this structure only electrons are shown. Now this bond I am drawing with this yellow color. These 2 bonds, as if these 2 bonds, okay, it is normal 2 electron 2 center bond. So 2C 2E bond, 2 center 2 electron. So look at it carefully. I am using different color. So this is one bond where one electron is coming from aluminium, another one is coming from chlorine. So these two bonds are 2C2E bond. But if you observe the next two bonds, which is shown with a pink colored arrow, in this bond, both the electrons are coming from chlorine. So this is coordinate bond. It is not normal covalent bond, it is coordinate bond, which is also clear in this structure, that is arrow sign is mentioned. So arrow sign means that both the electrons are coming from chlorine, and once it is already donated by chlorine towards aluminium, now these two electrons are shared equally between Al and Cl. So now it is behaving as covalent bond. So that is the feature of coordinate bond. But the important point is, now if you see in this dimer and compare with the monomeric structure surrounding aluminium, now what is the number of total electrons? Now surrounding aluminium, total number of electrons 2, 2, 2. So these three bonds are basically normal covalent bond, where two electrons, one is coming from Cl, another one is coming from Al. But this bond, which is coordinate bond, these two electrons, now you have to count. Now surrounding aluminium, there is total 8 electrons. In this way, electron deficiency is removed. And here one more point we have to see, that these two electrons and these two electrons, they are actually hovering over this free center, that is aluminium, chlorine, aluminium. So total 4 electrons, they are spreaded over this aluminium, Cl and aluminium. That means as if it is delocalized over this 3 center. So that is why it is called 3 center 4 electron type of bond. Okay. So in case of BeCl2, we have seen, that is I'm talking about beryllium chloride. There we have seen this type of dimer, but there it is not 3C4E bond, that is 3C2 electron bond. But in this case it is 3C4E. So total 4 electrons present in this 3 center. Okay. So this is the unique nature of this, that is structure of this dimer. Now here you can see the angles and the bond lengths. The bond length of these terminal bonds. So I'm saying terminal, these 4 bonds, 1, 2, 3, 4. And this chlorine, it is behaving as a bridging. So as if it is bridging bonds. Now if you look at this bond, it is 2.06 angstrom. But this bond is longer, 2.21 angstrom. And it is always so, even if you consider other structures, that is BeCl2, beryllium chloride dimer, there also you will see the same thing, because it is not normal 2C2E bond, it is 3C4E bond. So bond length is higher. Fine. Next we will see its properties. Aluminium chloride, its properties. As you can see in the picture, 2 types of colors you can see. Now depending on its purity, different colors that is it can appear. Aluminium chloride, sometimes it is called aluminium trichloride. When it is completely anhydrous, then only it is colorless in nature or white powder. But when it is turning gray or yellow because of its exposure to moisture, then it looks like this. Fine. It has pungent odor, it is hygroscopic, that means it has a tendency to absorb water. Corrosive to tissue, you shouldn't touch it by your hands. And it is toxic by ingestion. How it reacts with water, that is chemical properties. Now we have, that is the first one is physical property. Now we are starting chemical property. So this chloride of aluminium reacts dramatically with water, because we have already mentioned it is hygroscopic. So this type of explosive reaction is expected. It produces aluminium hydroxide, AlOH3. It has gelatinous type of nature along with HCl. Now aqueous solution of AlCl3, it is acidic in nature, because when we are having this hydrolysis reaction, in the product side there is formation of hydrochloric acid. Though you can say it should have some basic nature, but remember this acid is so strong that the basic nature of AlOH3 it is not so, that is HCl is predominating. So that is why ultimately the aqueous solution of AlCl3 it is having some acidic nature, and it is because of this presence of hydrochloric acid. Reaction with ammonium hydroxide. So with aluminium hydroxide, it forms, ammonium hydroxide, NH4OH, it forms aluminium hydroxide. So as if this anionic part is simply exchanged, AlCl3, now in place of Cl we have hydroxide ion AlOH3 and ammonium chloride. The next reaction for AlCl3 with sodium hydroxide. Now aluminium, it can react both with NaOH and ACl. Here we will see how it reacts with sodium hydroxide. So here also we are getting the gelatinous precipitate of AlOH3 in the previous reaction, that is reaction with water. There also we have seen when it reacts with water there is formation of this hydroxide of aluminium. Here also in presence of sodium hydroxide we are getting. So we are first getting it, and this is soluble in excess of NaOH. Now if you increase the amount of NaOH, then there is some formation of soluble complex. So first the white precipitate of AlOH3 that will be seen in the reaction container. Then when you add more NaOH, now it will be converted to some other compound which is complex type and it is soluble. And the name of this is sodium tetrahydroxoaluminate. Look at this reaction. When you have taken in this ratio 1:3, first there is formation of AlOH3, which is white gelatinous type of gel type of nature, gelatinous PPT, and along with formation of sodium chloride. Now this AlOH3, when it reacts with more NaOH, there is formation of this sodium tetrahydroxoaluminate. If I break this molecule, you'll be able to understand the cation and anions present here. So it is Na plus, and the anionic part is AlOH whole 4, 1 negative charge. So that is why we are calling it tetrahydroxoaluminate. It is a complex molecule. Oxidation state is obviously 3, and total 4 negative charges we are getting from HO minus, so that is why 1 negative charge extra, which is mentioned outside the third bracket, and that is balanced by the single positive charge we are getting from sodium. NaLOH whole 4, sodium tetrahydroxoaluminate. Now we can also write this reaction in a different way. Let me erase this. So if you take NaOH, that is when you are starting the reaction, then if you start with excess of NaOH, then it will produce directly NaLO2, and it is not a new compound, it is basically that is NaLOH whole 4, which we have already seen in the previous equation. This is a hydrated form of NaLO2. Now this reaction we have written here 1 molecule of AlCl3, 3, and then the product AlOH whole 3 further reacting with 1 more NaOH molecule. But if you write it directly, that is AlCl3 reacting with 4 NaOH, now the reaction it will be written differently. It is now NaLO2 and 2 H2O, 3 NaCl. And if you want to write the hydrated form, then it will be we have to write it in this way, NaLOH whole 4. So basically if I am writing in the form of NaLO2 and when I am writing in the form of NaLOH whole 4, basically I am writing the same thing. It is just whether you are writing the hydrated form or you are writing the anhydrous form. Okay, so NaLO2, it is the anhydrous form of NaLOH whole 4. Just you have to add water molecules, then only you will get this structure. So that is why we are saying that the hydrated form of NaLO2, it is NaLOH whole 4. Okay, so we are adding here 2 water molecules, so 4 hydrogen extra and 2 oxygen atoms extra, right? So you can write it in different way, but ultimately we are getting this type of salt. Reaction with Lewis bases. So this is also base, but it is not Lewis base. It is NaOH which is producing hydroxide ion. But Lewis base is something else. Lewis base means which can donate electron pair. So as we know that AlCl3 it is electron deficient in nature. There is total 6 electrons surrounding aluminium. So that is why it behaves as Lewis acid. It is Lewis acidic in nature. And when we are saying that it is Lewis acid, obviously it will react with Lewis bases. That is normal. So it behaves like Lewis acid, and that is why it can react with ammonia, phosphine, ammonia NH3, phosphine is PH3, carbonyl chloride is COCl2, carbon oxygen Cl2. So in this way, it can react with different types of Lewis bases. Here we have this example as if AlCl3, you know, this type of adduct or addition compounds, we write it like this with a dot sign, AlCl3 6 ammonia molecules. We can also write the equation. Here we have AlCl3 which is having total 6 electrons, so it is electron deficient. Now nitrogen is having lone pair, it is behaving as Lewis base which is donating this electron pair, and Lewis acid, the definition is electron pair acceptor, so it is accepting electron pair. So once this is already donated from nitrogen towards aluminium, sometimes it is also expressed with the arrow sign, and there is negative charge over aluminium because it has gained electron, and positive charge over nitrogen. Okay, same type of structure you can also draw with phosphine or other Lewis bases. Next, we'll see application part of AlCl3. Now it has several applications. The most important we always see in organic chemistry reaction, which is Friedel-Crafts reaction. It may be Friedel-Crafts alkylation or it may be Friedel-Crafts acylation. So in Friedel-Crafts alkylation or acylation, what we do, we take a benzene molecule or its derivative, and there is some RCl. Now this R is in any alkyl group, suppose ethyl chloride or methyl chloride, and in presence of AlCl3 catalyst, what we get one of the hydrogen of benzene. Now it is replaced by this R group, which is alkyl group. And when it is acylation, basically now RCOCl we have to start with, an acyl group, that is this RCO group, that will be inserted. But you need this type of Lewis acid AlCl3, and that is the application. So in this case, COR is introduced. But how it is acting as Lewis acid, that is what is the role of this AlCl3. If we want to understand that, just have a look here. Here we have taken this RCl, which is CH3CH2Cl, ethyl chloride. So in presence of AlCl3, what will happen? This chlorine that will be transferred towards AlCl3 as if it is accepting the chlorine in the form of chloride. Now when chloride is transferred towards this, it is changed to AlCl4 minus, and this part is now cation. Okay, and if I write it in this way, it is AlCl3, this is CH3CH2Cl, and we are getting this AlCl4 minus, there is a negative charge, and this is the plus. Now as here we have this, you can write it as in general form as if it is R plus. So this R plus, now it will be attacked by the double bonds of the benzene ring. So in this way the mechanism, if I write the mechanism, it will be like this. So this is the role of AlCl3. It is helping to generate the alkyl part. Okay, so this is the role as a catalyst, and remember it has to be anhydrous, because if it is not anhydrous, then electron deficient nature will not be there. Then how it can behave as Lewis acid? It has to be in electron deficient state, then only it can accept Cl minus from RCl, right? So remember, whenever it is acting as a Lewis acid catalyst, it has to be anhydrous. In hydrated form, it is not possible at all. Then as a catalyst in the manufacture of some other organic compounds, dyes, drugs, perfumes, widely used in manufacturing rubber, lubricant, wood, preservative, paints. In manufacturing some petrochemicals like ethyl benzene, alkyl benzene. So basically cracking is done with petrochemicals, and in cracking process, this AlCl3 is used. Some more applications as pesticides and in pharmaceuticals as a flux. The role of flux in metallurgy is to remove impurities in the form of slag. So when aluminium is extracted from its ore, then AlCl3 is used as flux, as antiperspirant, anti-hemorrhagic, as mordant or dye fixative. So mordant, the meaning of the word mordant means in dye industry, some substances are added for fixing the dye. So dye fixative, it is called dye fixative or mordant. So in the form of, that is as dye fixative, AlCl3 also has used, and now it is not anhydrous, because when we are doing dye fixative, obviously the condition is not hydrated. Sorry, the condition is not anhydrous because it is done normally in aqueous medium. So that is why there it is hydrated. It is not anhydrous. So these are the roles of AlCl3, that is application in different sectors. Now we solve this question, which is based on AlCl3, not just AlCl3, some other compounds of aluminium you can also see here. Total 5 statements, A, B, C, D, E. You have to find the correct statement out of these 5. It may be A or B, A, B, D, E, E, C, D, or all of these. So one by one we will read the statements. The first statement is saying that AlCl3 fumes in moist air due to its hydrolysis. So basically we have seen AlCl3, when it is reacting with water, there is formation of AlOH3 and also there is formation of HCl. And basically we see these fumes of HCl. So that is why when it is in contact with moist air means there is presence of moisture, that is H2O. So hydrolysis reaction is possible, and that is why we can see some fumes because of this. So this is true. Now A is true means this you can cancel. Next statement, aluminium metal is stable in dry air because of protective oxide layer. Now this is true, we have seen it, not in the last class, probably in some previous class. There is some oxide layer formation, that is Al2O3. This is the oxide of aluminium, and on the aluminium metal, on its surface there is layer of this oxide, and that is why once the oxide is formed, it will not be able to come in contact with other reagents, and as a result it can remain as stable. Okay, then so this is also true. Third statement, pp back bonding occur in halides of aluminium because of large size. Now here it is mentioned halides, so in general I am writing here AlX3 because it is mentioned as halide, it is not mentioned as chloride, so it may be any other halogen also. Now in this case it is saying that pp back bonding. Remember when we have seen BX3, that is boron, which is also from group 30. So in case of BX3, back bonding is very common, and when this X is fluorine, then back bonding is maximum. Why? Because fluorine is from second period and boron is also from second period. Now when it is second period, there will be 2p pi bond, which is quite good because 2p, it is compact in nature, they can come close to each other because of its small size. That means pi back bonding like this, when X is fluorine, it is very good, and once there is back bonding, I am writing as fluorine. Now it will be negative, it will be positive. So it means that when the sizes of the p orbital is very small, then only the back bonding is very effective. Now if X is changed from F to Cl to Br to I, gradually the pi bonding efficiency will be decreased because of increase in size. So good p pi back bonding is only possible when it is small and compact. That means if both are from both are from second period, that means it is using 2p orbital, then only pi back bonding will be effective. But here it is mentioned pi back bonding occur in halides of aluminium because of large size. But we have never seen this type of pi back bonding. That is this type of pi back bonding, just like as I have drawn for BF3. No, that is not possible because aluminium will be using its 3p orbital. And even if this X is F, then only it is 2p. But when you will change change the halogen from F to Cl, you have to now use 3p. Then for bromine, you have to use 4p. So gradually the size is increasing. So pi back bonding not possible. Basically in aluminium halides, pi back bonding, it is not there. It is only for boron. Fine. So p pi back bonding occur because of large size. This is completely incorrect. So this is not correct. It's false. Then the fourth statement, AlCl3 achieves stability by forming dimer. Now that we have already seen that remember this type of structure in the first slide of today's class we have seen, and mostly it remains in liquid in molten state, but state is not mentioned. It is simply written as it achieves stability by forming dimer, because when it is in this monomeric form, it is electron deficient. By forming dimer, electron deficiency to some extent reduced. So this is also true. And the last one, aluminium hydroxide, AlOH3, this is gelatinous in nature. Now this is also true. So A except C, all the other statements are correct. That means A, B, D, E, all these four statements are correct. Okay. This is related to aluminium chloride. Aluminium chloride exists as dimer, Al2Cl6. So when it will form dimer, if you take two of these, obviously it will be Al2Cl6. That is correct. In solid state as well as in solution of non-polar solvent such as benzene. So it is saying that aluminium chloride exists as dimer, which is Al2Cl6, in solid state as well as in solution of non-polar solvents such as benzene. So it is simply a statement is mentioned. It is not that we have to find it whether it is correct or incorrect. It is not like that. Simply a statement is given. And after that, the second statement is saying that in water, how it will behave. Because when it is in water, there will be some ionic nature change. So it will form some ions. So when it is in a simply solid state or in non-polar solvent like benzene, it is a dimer. But in water, what will happen? If you look at these options, in water, what will happen? AlCl3, when it actually undergoing hydrolysis, that is reaction with water, we have seen there is formation of AlOH3 and ACl, right? But that is not mentioned in any of these option, that is AlOH3 or ACl, right? So we cannot consider that reaction. Now come to the first option. It is mentioned here that it is forming alumina, that is oxide of aluminium and 6ACl. Now it is obviously not correct, even if you simply write two neutral molecules, because in other options B, C, D, you have some cation and anion. Only in the first option you have neutral molecules, but neutral molecules, this type of molecules are not found. When there is reaction with H2O, we have seen there is AlOH3 formation and ACl formation. So this is not correct. And the second one is saying that aluminium surrounded by 6 water molecules, 3 positive charge and 3 Cl minus. This is actually correct. Why? Because it is true that when you are simply considering AlCl3, it will have some covalent nature, but when it is in water, now it will behave differently. Now AlCl3, it is no longer covalent. It becomes ionic because of large hydration energy of Al3+. Now this Al3+ cation, it is surrounded by total 6 water molecules, and in this arrangement, energy is liberated. That means system is very stable. So this is aluminium 6 water molecule. It is nothing but this species. Okay. So this Al is surrounded by water molecules, and the chloride minus part 3 chloride per aluminium 3+, that will be remaining as counter ion. And why this is forming? What is the driving force? The driving force is when this type of arrangement is occurring, there is large amount of energy released, which is hydration energy. The more energy released, the more negative is the value. And here charge density is very high. Al3 plus charge is high. So this system, if it is formed, it will be very stable. That is the driving force. So option B is basically the correct option. And in the last statement, last option, it is simply mentioned Al3 plus 3Cl minus. But see, there is no mention of water molecules. So without molecules, the existence of Al3 plus 3Cl minus, it is not possible, because when it is not in presence of water, it will not remain in this type of dissociated form. It is not ionic. So how this can be true? And here it is AlOH whole 6 3 minus, as if 6 hydroxide are surrounding aluminium. But that is not the case. 6 water molecules surrounding aluminium, and water molecules are neutral. So this 3 plus charge, it is still mentioned outside. So option B is the correct option. When it is in water, it will not remain as free Al3 plus ion. It will be forming the ion AlH2O whole 6 3 plus and chloride ion as it is. Heating an aqueous solution of aluminium chloride through dryness. Suppose you have taken some aluminium chloride aqueous solution and you are heating in such a way so that ultimately all the water part is evaporated and it is completely dry. Then what will form? Now in the first slide of today's class, in the properties section of AlCl3, we have seen how it reacts with water. But simply reaction with water, that is not that will not give us answer, because first it is saying that heating an aqueous solution to dryness. It is completely different thing is happening here. So first, if you simply consider reaction with water, that is hydrolysis, then this reaction we have already seen. But when you are heating to dryness, now what will happen? This part, which is actually the aluminium containing part, when you are further heating it in such a way that it is completely dry, now it will form Al2O3, water molecules will be removed. So it is, if it is 2 moles of AlOH3, 1 mole of Al2O3 will be formed. So correct answer will be option 3. Next question, again related to AlCl3. Hydrated AlCl3 is used. So it is application oriented question. Hydrated AlCl3 is used catalyst in cracking of petroleum, catalyst in Friedel-Crafts reaction, mordant. Remember, mordant is difixative agent. All of the above. Now, I have already said that whenever it is behaving as catalyst, it has to be anhydrous, because only in anhydrous condition it can behave as Lewis acid. If it is not anhydrous, it will not behave as Lewis acid. And if it is not behaving as Lewis acid, it is not possible to, it will not be able to behave as catalyst, because the catalytic nature, remember the mechanism, it has accepted one chloride ion and from RCl, that is I'm talking about Friedel-Crafts reaction, and after accepting one extra Cl minus, now it is converted to LCl4 minus. Now this is possible only if it is anhydrous. If it is not anhydrous, it is not possible. So hydrated AlCl3 you cannot use as catalyst. So all of the above, this is also not correct. Only option left is mordant, that is difixative. Which one of the following correct statement? Now this question, it is not only have aluminium, it is also having boron containing compound and beryllium. So I'm discussing this question now because it is basically mixture of two chapters, you can say, that is S block chapter and P block chapter. So we have now complete idea about aluminium chloride. So to solve this question, basically we have to have the knowledge of aluminium chloride. And as we have already finished it, so I'm discussing this. Okay. So boric acid, H3BO3, remember? We have to find correct statement. That means out of 4, only 1 is correct, rest of the 3 incorrect. Boric acid is H3BO3 and we know it behaves as Lewis acid. It is not Bronsted acid. That means it is not protonic acid. It can accept, if I am writing it like this, it can accept one OH molecule from water. The reaction is already there. So this equation you have already seen before. If you write water molecule like this, it will accept this OH part itself will be converted to BOH whole 4 single negative charge. And this part will be removed as H plus. So it is accepting HO minus, it is accepting electron density. So it is behaving as Lewis acid. It is not correct statement, it is false. Then beryllium exhibits coordination number 6. Beryllium, which is Be. It is from group 2. It is the first member of group 2. Now to show oxidation, coordination number 6, it has to have d orbital. Okay, but as it is from second period, beryllium is from second period, so it cannot have d orbitals, and if it is not possible, then increase in coordination number, that is also not possible. Maximum it can have coordination number 4, but not more than that. So this statement is not correct. Now the third statement, we have to know why C and D, these two are correct. Chlorides of Be and chloride of Al have breached chloride structure in solid phase. So in solid phase, we have seen there is some octahedral type of structure, but still there is some bridging. That is, aluminium is connected by two aluminium connected by chlorine. So if you are considering dimer of aluminium, then it is simply like this. If you are considering the octahedral arrangement, then 2 more chlorine will be there. But whatever it is, this bridging chlorine is present. And if you consider beryllium chloride structure, in the S block chapter, you can check it. This type of structure we have seen. That means here also we have, in solid state, bridging chlorine. Chlorides of both these elements have reached chloride structure in solid phase. So this is also true state. And the last statement, B2H6 2NH3. Now B2H6 is diborane, that is the dimer of BH3. It doesn't exist as monomer. It is always like dimer B2H6 because to remove its electron deficiency. And as it is having some Lewis acidic nature, it will form some type adduct type with the Lewis bases such as ammonia. So you can see that. But it is saying that it is known as inorganic benzene. But is it true? Actually, if you directly look at this formula, it seems as if it is not true, because inorganic benzene or borazine is B3N3H6. But here it is not looking like B3N3H6, right? But actually, see, if you consider this structure, if you consider this equation, then only you will be able to understand. So this equation, again, I am showing, it is already shown before in the properties section of diborane, where in the heading of how it reacts with ammonia, then the same equation you have already seen it. Once again, we will see it here. 3 moles of B2H6 with 6 moles of NH3. That means here the ratio is 1:2. The same ratio you can also see here. So when it is treated, that is, these two are mixed like this and it is heated, first there is formation of this type of cation, BH2 unit with 2 NH3 positive, BH4 minus. But ultimately when it is heated at 473 Kelvin, finally we get B3N3H6. So indirectly it is true. Maybe it is not directly correct, that it seems as if it is not correct. But actually B2H6 2NH3, ultimately it is forming this borazine or inorganic benzene. Why it is called inorganic benzene? Because it has, if you consider its structure, it has similarity with the benzene structure, and that is why it is called inorganic benzene. Because inorganic, why? Because there is no carbon, so that is it is inorganic. Okay, so the last statement is also correct. Only this sorry, this is not correct. Sorry, completely. I thought it is only we have to choose incorrect statement. That is not the case. We have to choose correct statement. And B2H6 2NH3, suppose if we have to, that is already it is mentioned, it is correct statement. And we have seen that boric acid, which is protonic acid, it is not correct, it is wrong. Then beryllium exhibits coordination number 6, that means it is also wrong. Now out of these two statements that is left, only one will be correct. Now chlorides of both beryllium and aluminium, we know that it is already correct. So that's why this will be the only correct answer. Okay, the last one is not correct because B2H6 2NH3 in the adduct form we cannot say it is correct, though it is true that when we are heating it, then it will be converted to B3N3H6, which is actually borazine or inorganic benzene. But suppose if you are getting any question where more than one statement is correct, so directly we cannot say that this is completely wrong, because ultimately B2H6 to NH3, this if you consider the ratio, mole ratio, it will ultimately lead to this structure because their temperature is not mentioned. Okay, so from that point of view it is correct, but as out of 4 statement we have to choose only one correct statement, it cannot be more than one. So that is why option C, this will be the correct answer. Okay, so we have finished AlCl3, that is aluminium chloride. Now we will start alum. Now before going to the actual discussion of alum, first we have to know double salt. So what is double salt? Double salt is sometimes we mix two salts and they form a structure, but if you dissolve it in water, whatever cations and anions are present, all of them will show their characteristic. So in double salt, there is more than one cation, there is more than one anion, not necessary, but at least more than one cation should be there. And when you are dissolving it, all these cations and anions individually, they will show their property. So here the general formula for alum you can see X2SO4, that is sulfate of X, where X is any monovalent cation. It may be sodium plus, potassium plus, or ammonium plus. And then dot, double salts are written in this way with a dot sign, M2SO4 whole 3. Now from the formula you can understand it has to be monovalent because sulfate is having 2 negative charge. Now to balance this 2 negative charge, if it is that is the cationic part is written as X2, that means it has to be monovalent. Now look at this formula, M2SO4 whole 3. So total 3 sulfate means total negative charge 6 negative, that means total positive charge must be plus 6. You have only 2 cation, so each cation should be containing 3 positive charge. So that is why it is trivalent. So the second part, M2SO4 whole 3, it is containing trivalent anion, and it can be Al3 plus, Cr3 plus, Ab3 plus, etc. Now when there is presence of Al3 plus, then it is a type of, one of the type of alum. But nowadays this use of this term is so common, that is containing Al3 plus. So though this is a general term, that is when we are saying alum, we should consider this formula. But one of these formula may be containing Al3 plus, but we nowadays alum is also used by default that for this Al3 plus containing double salt. So see here we have different types of alum. Alum is not that you will have only, depending on what type of X and N present, you can have different types of potash alum, chrome alum, soda alum, ferric alum. So it depends on what is your X, see X, or what is your M. In this case we are saying it's potash alum, and potash alum is our actual topic of discussion. So it should be pronounced as potash alum because there only you have aluminium. Though soda alum there is also this one, but this is more common. Okay, so when we say alum, sometimes by default it means potash alum, though alum is more general term. Okay, so in potash alum we have K2SO4, L2SO4 whole 3, 24 water molecules. Basically 24 water molecules is common for all. Here we have potassium and chromium 3 plus, sodium aluminium 3 plus. Here we have ammonium and iron 3 plus. Ferric alum. Ferric means 3 plus. Ferrous is 2 plus. Okay. Now if I write it, that is total number of potassium is 2K plus, total number of sulfate is 1 and 3, 4 SO4. Total number of aluminium 3 plus is 2Al3 plus, and there is 24 water. So I am writing it individually. So when you will dissolve it in water, you will get, that is, it will show the properties of K plus, SO4 minus, Al3 plus. So this is the feature of double salt. Whenever you dissolve it, all the individual cation anions, they show their individual appearance. Fine. Now, if you look at this formula, if you take 2 common, then it will be only 1 potassium, only 2 SO4, then only 1 aluminium 3 plus and 12 water. So sometimes the formula, it is also written as K dot Al 2 SO4 and 12 water. So sometimes it is also written in this way. Now, as I have said that by itself, alum sometimes refers to as potash alum. That is, suppose I am saying alum, it means potash alum. With the, because it is so common, with the formula KAlSO4 whole 2. So see here it is written in different way. Both are basically correct. This is also correct if you write it in this way. Individually, the positive charge, negative charge, if we balance, it will be K2SO4, L2SO4 whole 3, 24 water. But if you take 2 common, then it will be like this. Now alums in general, they are more soluble in hot water compared to cold water. And as I have said, the feature of double salt is that they exhibit the properties of all the constituent ions. So here constituent ions are potassium plus, sulfate 2 minus, and aluminium 3 plus. Okay, and it looks like this potash alum. Preparation. If you consider mineral of this, so it is naturally obtained from alum K. Now look at the formula. It is basically the same that you have seen. 12 water molecules, KAlSO4 whole 2, 12 water molecules, which is naturally occurring sulfate minerals. But if we consider that is man-made method, industrial scale, then how we can make it? Now to make potassium industrially, we have to dissolve equimolar mixture of hydrated aluminium sulfate and potassium sulfate. Okay, so hydrated, why equimolar mixture? Because if you look at the equation, ultimately this is the formula. Here both are basically 1:1. That is individual if you consider K2SO4, potassium sulfate. Individual if you consider aluminium sulfate. These are the formulas. So we have taken it 1:1. Equimolar mixture of hydrated aluminium sulfate, that is this one, with 18 water molecules, and potassium sulfate with no water molecules in minimum amount of water, and there is a little sulfuric acid which is not directly entered in the reaction, but ultimately it is required, and then subjecting the resulting solution to crystallization when we get finally octahedral crystals of potash alum. The reaction is very simple. There is no change happening, only some, you have to put some dot signs. And this 18 water, 6 water together we have written as 24 water molecules. So this is the preparation method. Properties. White crystalline solid, you have already seen its picture. Now it is acidic in nature. Why? Because when it is undergoing hydrolysis, we know there is already presence of SO4 2 minus. So in presence of water, it can form sulfuric acid. So that is why it will have some acidic nature, and its acidic nature is also proved by the color change of blue litmus to red color. Water solubility is there, but not in alcohol. Melts at 365 Kelvin on heating. Now, if you, it is a melting temperature 365, but if you bring it to 475 Kelvin, now potash alum loses water of hydration. See, all the 24 water molecules are removed, and there is some swelling up. That is, the substance is swelling up. and the solent mass is called burnt alum. So burnt alum is this part. Now, if we further heating it red hot, that is, if we go beyond 475, more than this red hot temperature, now there will be decomposition. So these two parts now, see how it is decomposed. This part there is no change, but Al2SO4, it is as if cleaved to Al2O3 and SO4 is changed to sulfur trioxide. Okay. Now another reaction, how it reacts with ammonium hydroxide. When you are treating potash alum with ammonium hydroxide, then we get K2SO4 is now removed and we are getting ammonium sulfate salt. A new sulfate salt we are getting, 24 water removed, and the fate of aluminum is now it is hydroxide, aluminium hydroxide. Okay. Application part. Now, just like AlCl3, alum is also having versatile applications in purification of water by settling dissolved sediments. So there is some, if you consider the mud particles, when we add alum, there is presence of Al3 plus, and this Al3 plus, it has some coagulating property. It can coagulate the mud particles and ultimately the water will be cleared. This is very important application. That is, naturally we can purify water. Then waterproofing. Suppose in textile industry, we want to make some fabric waterproof. Then also it has application. Pickling agent to keep pickles crisp, flame retardant in dyeing, printing fabrics, paper, leather, tanning industries, as adjuvant in vaccines. So adjuvant, it means that is the meaning of this term is it enhances the immune response. Okay, so alum is also having application in that. As deodorant rock. So as you have seen its appearance, it appears as if it is a white type of rock. It can be used as natural deodorant. It has that property. Okay. Antiseptic and astringent, and because of its antiseptic property, aftershave, that is application as aftershave is very important. Styptic pencil. Styptic pencil is also used mostly after shave when we there is some minor cuts to stop the bleeding. Okay. So styptic pencil is basically the pencil made of alum. It's a white type of pencil. Ingredient in some brands of toothpaste, speed up the hardening of concrete plaster and as a catalyst also in different chemical reactions. Fine. So related to potash alum, we have this question. What is the chemical formula of potash alum? So remember, KlSO4 whole. If you actually write the formula, that is the first formula that we have seen, it is Al2SO4 whole 3. Simply as if I am writing two individual salt with a dot sign and then there is 24 water. But here we do not have any 24 water. But if you take 2 common, then it will be Kal4 sulfate. Now it will be total 2 sulfate. So in this way you can remember it. And 24 will be now 12 water molecule. So it is matching with first option, right? So if you simply 2 is taken common, we are getting this formula. So option A is the correct option. Application oriented question. Alum helps in purifying water. Remember the first application in the previous slide we have seen. But how it does so? It is true that it can be used for purifying water, but how? What is the mechanism? It forms a silicon complex with clay particle. Now, where from silicon is coming? It cannot be true at all, right? The sulfate part which combines with the dirt and removes it. It is saying that the sulfate part of alum, but it is already mentioned in the previous slide we have seen that aluminium 3 plus is basically responsible for coagulating. So the next statement, aluminium which coagulates the mud, it is not the anionic part which is helping in coagulation, but the cationic part. So this should be the correct option. And the last one is saying making mud water soluble. So mud is actually the impurity and it is saying that it is making mud water soluble, because mud is not water soluble, it is in suspended condition. That is why the water is not looking transparent. But making it water soluble, it is not that impurities are removed. So it cannot be true. So what is happening here? If you look at this picture, first there we have impurities in water. Suppose these are the mud particles. When we are adding this alum, now this alum, this yellow orange color, they are helping in coagulation, and finally what will happen, the size of these particles will increase in such a way ultimately they will sink the bottom. And once they are separated and sink to the bottom as in the form of precipitate, we can filter the water. Okay, and it is because of this high charge of aluminium 3+ that it helps the small particles, mud particles, which are before in suspended state. Now they will group together, and when they are grouped, they are coming close to each other, they are forming large particles and they will sink, and then only we can decant or we can filter the clear water. So it is not that making the mud water soluble, it is completely removing the mud water, and that we can do by filtration. Fine. So some question regarding group 13 here we have, though I will not start it today. So in the next class, we'll discuss 2 to 3 questions, which is based on group 13, and also some knowledge of S block will be required. And then we'll proceed to the next group, which is group 14. Okay. So we are ending the session here. Thank you for listening.